Hello everyone, I'm Rajasri, Assistant Professor, Department of Electrical and Electronics Engineering, working at MLR Institute of Technology, Hyderabad. And in today's lecture, I'll be discussing step-down choppers. Previously, we have seen step-down choppers with resistive load, and here in this lecture, we'll be discussing step-down chopper with RL load. And here in RL load, we'll be observing both continuous current mode of operation as well as discontinuous current mode of operation. And here, if you see, there is a transistor which we are making use of, and as I told you, we can either make use of a transistor or an IGBT or a GTO or power MOSFET instead of transistor, and this switch is being connected between supply as well as load, and here we are making use of RLE load. And RLE load represents practical DC motor drive. And here we are also making use of a freewheeling diode in order to obtain maximum advantage of inductive load. And here, if you see, we have provided the base drive. Let us observe the waveforms for this particular circuit. Initially, we have provided the base drive right from the instant called 0, from 0 to delta t. I have provided the base drive for the transistor, and the moment when I provided the base drive, the transistor starts conducting. And if you see, since I have provided the base drive, transistor is on and it is conducting current through the load in this direction. And when the transistor is on, the supply voltage is connected to output voltage, and that is how we are getting the output voltage waveform right from 0 to delta t. As long as the transistor is remained on, we are getting the output voltage with magnitude of Vs, supply voltage magnitude. And if you see, transistor is remained off from delta t to t. That is, we have withdrawn the base drive over here. There is no base drive provided, and that is how transistor remains off from the instant delta t to t. And the moment it reaches t, again we have provided the base drive, and that is how supply voltage is connected to output voltage, and here we are getting the output voltage waveform right from this instant called t to t plus delta t, and the cycle repeats. And that is all about the output voltage waveform. And now moving on to the output current, and if you see the output current, here we are making use of, since we are discussing continuous current mode of operation, the value of the inductor which we are making use of is usually very large. It is assumed as large value of the inductor, and that is how the moment when base drive is provided for the transistor, at that instant transistor is on and it started conducting current through the load in this direction, and the current starts building at a slow rate. It is because of the presence of the inductor in the load, and inductor, it does not allow any sudden changes in the current. So that is how it builds at a slow rate. And hope you understood the difference in the waveform compared to that of resistive load. It was just similar to that of the output voltage waveform, whereas here in inductive load, current waveform is different from that of the resistive load just because of the presence of the inductor, which does not allow any sudden changes in the current. And that is the reason here current is building at a slow rate, and initially the current is I minimum, and the moment it reaches delta t, the current became I maximum. This instant we call it as I maximum, and the moment it reaches maximum value of the current, here we have withdrawn the base drive for the transistor. That means right now the transistor is being turned off. That means when the transistor is off, usually there should be no output current through the load. Whereas now, if you see, because of the presence of the inductor, during positive half cycle, current flow through the inductor was there, and during which it has stored certain amount of energy with the magnitude VL is equal to L into di naught by dt. And because of this voltage which is being stored by the inductor, it tends to maintain the current flow in the same direction according to Lenz's law. And that is how here the freewheeling diode which is connected across the load will be getting forward bias, and then it starts conducting current through the load. Whatever the energy stored in the inductor itself is driving the current through the load right from this instant called delta T to T. Delta T to T. And whatever the energy stored in the inductor is slowly getting reduced. That is how the current waveform is also coming down, and the moment it reaches T, it is not at 0 but almost 0. By this time, we have provided the gate base drive for the transistor again from T to T plus delta T. That is how transistor has come into the on state, and again it is driving a current through the load, and because of the presence of the inductor, current is building at a slow rate and becoming maximum at this instant called T plus delta T. And the moment it reaches T plus delta T, we have withdrawn the base drive, and that is how transistor is off. But there will be certain amount of energy already stored in the inductor, and it tends to maintain the current in the same direction. And that is how, because it is driving the current through the load, the energy stored in the inductor is getting reduced. So that is all about the output current waveform, current through the load. And now let us check out the current waveform for transistor current. Transistor current, if you see, the current flowing through the transistor is same as that of the supply current. See, supply current is equal to that of the current which is flowing through the transistor as well. So this is one and the same, which is common. That is, transistor current as well as supply current is one and the same. And as long as we are providing the base drive for the transistor, transistor is remain on and it is conducting a current through the load. And here, if you see, current is conducting through the transistor, and again it is remained off the moment when we withdraw the base drive at this instant called delta T. So that is how the current through the transistor or supply current is becoming 0. And again at this instant called T to T plus delta T, the transistor is conducting current through the load, and that is how we are getting the waveform at these two instants, and the cycle repeats. And then moving on to the freewheeling diode current. Freewheeling diode current, that is how long the freewheeling diode is conducting, that long we will be getting the waveform across the freewheeling diode. And if you see, freewheeling diode is coming into picture at this instant called delta T to T. See, the moment at delta T, when we have withdrawn the base drive, inductor voltage across the inductor is making freewheeling diode forward bias, and that is how freewheeling diode is conducting from delta T to T. And again from T plus delta T to so on. The cycle repeats. This is the waveform across the freewheeling diode. And now moving on to the step down chopper with RL load for discontinuous current mode of operation. And previously we have seen continuous current mode of operation. If we are making use of a large value of the inductor, in that case output current through the load will be continuous. Whereas now here, since we have chosen the smaller value of the inductor, in that case we can obtain discontinuous current mode of operation. And let us check out the waveforms for this step down chopper with RL load for discontinuous current mode of operation. And here, the moment when we provide the gate drive, that is from 0 to delta T, we are providing the base drive for this particular transistor, and hence it got turned on. And when the transistor is on, see, this is how it is driving the current through the load. It is driving the current through the load. And when transistor is on, supply voltage is connected across the load, and that is how we are getting the output voltage right from 0 to delta T. 0 to delta T, and that too of magnitude V0 is equal to Vs. V0 is equal to Vs. And we can also explain this in other way, like V0 is equal to, since current is flowing through the load, V0 is equal to I0 into R. Anyways, here Since transistor is turned on, supply voltage is connected across the output, and that is how we are getting the output voltage right from this instant called 0 to delta t with magnitude Vs. And the moment it reaches delta t, we have withdrawn the base drive, and hence transistor is turned off. And since we are making use of a inductor, and if you see, because the transistor is turned off, the moment when we withdrawn the base drive, since the transistor is turned off, from delta t to t, there is no output voltage waveform. Here, V0 average is equal to 0. And again, at this instant called t, from t to t plus delta t, again we have provided the gate drive for the transistor, and again it has got turned on, and thereby we are getting the output voltage right from this instant called t to t plus delta t with magnitude Vs. And later, coming to this is how the output voltage looks like. And coming to the output current, it is present right from 0 to delta t. That means since we have provided the gate drive from 0 to delta t for the transistor, that is how transistor started conduction current right from 0 to this instant called I maximum. The moment it reaches maximum value at this instant called delta t, from 0 to delta t, because of the presence of the inductor, current through the load is building at a slow rate, and it is becoming maximum at this instant called I maximum delta t. And the moment it reaches delta t, here we have withdrawn the base drive, and that is how transistor remained off. And since transistor is off, whatever the energy stored in the inductor will tend to maintain the current flow in the same direction, and because of the voltage across the inductor, this particular diode will be forward biased and it starts conducting current through the load. And since inductor is providing the energy, the current through the inductor is getting reduced, and it is almost becoming 0 by the time the energy stored in the inductor is completely dissipated, and it becomes 0 at this instant called t1. And if you observe in continuous current mode of operation, current will never get 0, and it will be, the moment it reaches 0, it will be triggered again and the cycle repeats, thereby the current flow through the load will be continuous. Whereas here, because the value of the inductor which we have chosen is less, that is the reason here we will be obtaining discontinuous current mode of operation. And from instant t1 to this instant t, the current through the load remains 0. That is the reason we call it as discontinuous current mode of operation. And now, coming to this instant called t, again we have provided the base drive for the transistor, and that is how transistor again started conduction current through the load, and current is building at a slow rate because of the presence of the inductor, and it is becoming maximum at this instant called I maximum. And the moment it reaches I maximum, that is t plus delta t, again we have withdrawn the base drive for the transistor, hence transistor is off. And because of the transistor is off, whatever the energy stored in the inductor is making diode forward bias, and thereby it is maintaining the continuity of the current flow till next instant. And it is completely driven the energy stored in the inductor, and hence it is becoming 0, and the output current will be remain 0 for some period of time. Hence we call it as discontinuous current mode of operation. And this is all about the I0 current flow through the load. And now coming to the transistor current. Here in transistor current or supply current is one and the same. See, here the supply current is what flowing through the transistor. That means supply current is equal to transistor current. So here IS or IT will be indicated right from this instant called 0 to delta t. And the moment it reaches delta t, since we have withdrawn the gate drive, the transistor is no more on, so we don't need to indicate the current through the transistor after delta t. And it is conducting from 0 to delta t itself, and it is remained off from delta t to t. and again it is triggered at the next instant called t, from this instant to this instant. And the moment it reaches t plus delta t, here we have withdrawn the gate drive. That is how transistor is off. So it is no more conducting. So we don't need to indicate the waveform through the transistor. And coming to the current through the freewheeling diode. Current through the freewheeling diode, it is present from the moment when we withdraw the base drive, the freewheeling diode comes into picture and it takes over the current flow through the load. So the moment the base drive is withdrawn for the transistor, that is from delta t to the next instant. How long it will conduct? As long as energy stored in the inductor is completely dissipated. And once the energy stored in the inductor is 0 at this instant called t1, freewheeling diode will also get turned off. So that is the reason here waveform is indicated. The waveform for the freewheeling diode is indicated right from this instant called delta t to t. And again, during the other period, that is from t plus delta t, we have withdrawn the base drive for the transistor. And again transistor is off, and at that moment the freewheeling diode came into picture, and thereby it is driving the current through the load as long as energy stored in the inductor is present. Once it is exhausted, the current through this particular freewheeling diode is also 0 because it gets turned off. It will be no more forward biased. And this is all about the step down chopper with RL load for discontinuous current mode of operation. And now step up chopper with RL load will be the next topic. Thank you.